hiking adventures I'll tell you about. So some of you may recognize this one. This is Hemden Hollow. We've actually talked about this before briefly. This is a hike that you can access two ways. If you float the Buffalo River through the summer, spring, summer, fall, there's a point if you float from like Still Creek to Kyle's Landing, that's a very popular float. You can pause and you can actually hike this portion of the trail. It's very flat, or you can park. The trailhead is near a place called Compton. You can park there, and the hike is very vertical if you want to hike it that way. So down the whole way to the waterfall, up the whole way back to your car. But this is the waterfall that you'll see. And if it's not been raining a lot, the waterfall is nothing exciting to see. It's more like a little trickle of water. But nonetheless, it's a really awesome hike in the Buffalo River area. And you will often see, I don't know, I say often, I've seen it before and I've heard somebody else say they've seen it before. People will stretch a tightrope line thing across up here and they'll walk it. So you never know if you're going to run into some entertainment when you get down to the bottom of people hanging off. I'll draw a little person hanging off of this rope. Okay. You never know if you're going to see that. I will never do that, but there are people who like to do that. So there's that. Oh, I don't have my chat up. I've never seen that before. Wow. Yeah, I have seen that. But the other trail I want to tell you about is called, come on, scroll up, the Lost Valley Trail. This is also in the Buffalo National River Wilderness area. Now I know you're thinking, that's not a trail, that's a cave. And the trail leads to a cave. And inside the cave, you will find a waterfall in the cave. And I don't have a picture of the waterfall in the cave, but you have to hike back into the cave quite a ways. And if you are claustrophobic in any manner, in any measure, do not hike this, because the walls literally close in on you pretty good. You have to get on your hands and knees and crawl a little bit. And then it opens up into this area where there's a waterfall in the cave. So how many of you would love to go do that one? How many of you are like, you could not catch me dead in there? It's pretty amazing though. So there's my husband. We just took a picture from inside the cave. I think we were on our way out. I'm not sure, but really awesome hike. The hike is actually very beautiful. And then the cool cave and waterfall in the cave at the end. I would say take a headlamp, obviously, or you will never make it out. And then you will get lost in the cave forever and you'll die there and strange things will probably eat you. So, all right, let's talk about what we came here to talk about, acids. You like my question? What do you think of when you hear the word acid? Many people think of different things. You got that from a movie? Yeah, have y'all seen The Descent? That's the cave, creepy cave movie. I don't watch scary movies anymore because I'm an adult now. And I used to watch them when all my friends wanted to, but I don't anymore. Okay. What do you think of when you hear the word acid? Some people think of citrus fruits like citric acid, very acidic foods. Some of you have to stay away from foods like this if they upset your stomach. When I was pregnant, I don't know if this was a thing, but I love limes. I love like club soda with a lime in it. So I could not get enough of citric acid. My mouth is watering right now thinking about it. Some of you think of like laboratory acids. You think of like Breaking Bad, that kind of use of acids to do crazy things. Or we use acids a lot in the labs. We've used them this semester in the Chatelier's principal lab. Some of you think of recreational uses of acids, and that is not what we're here to talk about today. So do not think of that one. You are all future health professionals, okay? You're all better than that. But what is the definition, the chemical definition of an acid? It is a chemical or a compound. So we'll just say that donates an H plus, a hydrogen ion, okay, to it's a compound, it's a chemical. It donates a hydrogen ion to another molecule. That's the simple chemistry definition. And when we think about the hydrogen ion for a second, I want to draw your attention to that. Think about a hydrogen ion. What is a hydrogen ion? Well, we know hydrogen. I'm going to draw a picture of it. Here's the nucleus. And actually, I'm going to draw just a proton in the nucleus. Here's the nucleus, one proton. And we know in the electron cloud, there's one electron. That's hydrogen, right? Well, if it's a hydrogen ion, meaning it has lost its electron, all we have is this, right? We just have a proton. So that is why we call a hydrogen ion a proton. Those words are synonymous because that's the only thing present in a hydrogen ion. So you will frequently say, we're donating a proton, or who's giving the proton and who's accepting the proton. Okay, when we talk about acids and bases this way. Because of this, acids are sometimes called proton donors. Proton donors. On the driver's license, it says proton donors. All right. Here's a picture of an acid-base reaction. So we have HCl and we have water. And you see their Lewis structures, and then you see these space filling models that are rainbow colored, showing you kind of the electron rich portion, which is red, and the electron deficient portion, which is the blue side. And then on the product side, we see after the proton or after the hydrogen ion is transferred, what products we create. And we have water here because all acid-base reactions happen in aqueous solution. So in aqueous solution, all of these things happen in aqueous solution. So water is always present. The hydrogen ion is donated to water here. So to water. And what do we create? So here's water, and then here is water with the added hydrogen ion. So we have water on the left side, then we have water with the hydrogen ion on the left side. Does anybody remember the name of this? This was actually a polyatomic ion that you were supposed to memorize, or at least know. Thank you, Kathleen. Hydronium. Hydronium ion, which is H3O plus. Okay. But H3O plus and H plus are used interchangeably. So that's confusing, right? Essentially, the hydrogen ion can pop on and off the water. And so because of that, you never know if it's on the water, if it's off the water. So H3O plus or just H plus, we just use those words interchangeably, just so you know. So if I say hydronium or H plus, or if I say find the concentration of hydronium or find the concentration of H plus, that's just one and the same, okay? And then what's left over from HCl? HCl is the one who gives the hydrogen ion here. Water accepts it. What's left over is just Cl minus on the other side as well. So this is an example. Again, all acid-base reactions happen in aqueous solution. So let's look at another example. What happens when I dissolve a different acid? Here we have HNO3 in water. What happens anytime you dissolve an acid in water? Here's what's going to happen. This happens to be nitric acid. We just looked at an example up here with hydrochloric acid. HCl is hydrochloric. And this is nitric. Okay, we call it that because the base molecule here is nitrate, another polyatomic. So this is nitric acid. So if this is the acid, and we know acids are proton donors, it's going to give away a hydrogen. So we're going to take this hydrogen off and we're going to donate it to water. So what's going to be left over? We're going to create H3O plus now. There's our hydronium ion. And what's left over from the acid is just NO3 minus, that nitrate anion. So that's what happens. Anytime you dissolve an acid in water, when you just have acid and water, the acid will donate the hydrogen, the water will accept it, you'll create hydronium, and then you'll have the anion version of the acid left over. So the H plus attaches to the lone pairs on water and makes H3O plus, which we've seen. Okay, it attaches to the lone pairs on water, and we're gonna look at that, and I want to look at that in a little more depth. Think about when you create a bond. What do we know a bond is made of? If I have atom A bonded to atom B, what is in this bond? Electrons, right? That's 2 electrons. Well, if I'm trying to make a bond between H plus and on water here, That's what we've been looking at so far. H plus has no electrons to bring to the table, okay? It has none to donate to this bond we're going to form. So anytime you're forming a bond here, you have to have a lone pair from another atom so that this hydrogen can bond to that. If you only have one single electron or no lone pairs on a molecule, you have nothing for the hydrogen ion to bond to. Water here has to bring both electrons, 2 electrons, to the table to form the bond. Does that make sense? The base, essentially, what's accepting the hydrogen ion, has to supply both electrons because the hydrogen ion just doesn't have any. So keep that in mind. You can also, sometimes we'll just omit water and we'll convey the same idea, the same thing that's happening to the acid by just writing the reaction for what we call the dissociation. Dissociation of the acid. Here it's nitric acid, but you could do this with any acid, okay? How would that look? Well, if we take water, here we have water here. We just take water out of the equation. All we have is HNO3. We're going to draw it dissociating into H plus and NO3 minus, okay? Anytime you see a reaction like this, that is called the hydrogen ion is dissociating from the acid it was originally bound to. We could draw that for HCl. What would be our products? If you dissociate HCl, you should get H plus, Cl minus. What about H2SO4? This is sulfuric acid. And just do it for one hydrogen here. Here we have 2 hydrogens. Just do it for one hydrogen here. Dissociation of one of the acidic hydrogens. What would you get? H plus, and then what's left over? You should have HSO4 minus is left over. Okay. So if I tell you to write the dissociation of whatever acid, that's what I'm saying. You just write the acid and then you write it with losing one hydrogen or one proton. Okay, questions so far? Questions on what happens when you dissolve an acid in water? Questions on how an acid dissociates? Okay. Another thing to know about acids, I have to be really careful when I teach this chapter because I say the word acid so many times. And if you have a slip of the tongue, you can quickly become PG-13. All right, many polyatomic ions exist as acids, and several donate multiple protons. Okay. So far we've just seen one proton, it losing one proton, but you have acids that can donate multiple. So we name them different ways, by the way, depending on how many protons they could give away. Hydrochloric acid, we call it a monoprotic. Mono indicating just one proton to give away. It's in red. Nitric acid, guess what? Also monoprotic. Mono meaning one proton to give away. But sulfuric acid, which is the H2SO4 we just drew up above, we call it diprotic because it has 2 hydrogens, H2SO4, and it can give away both of those. Okay, so di meaning it's got 2 protons. Guess what? Phosphoric acid has 3, so we call it triprotic, right? I can't think of an acid that would have more than that. There might be some organic acids that would have multiple, more than 3 possibly, but none of these are your inorganic acids. We'll explain the difference in a second, but so you mono, di, and triprotic. However, they always lose 1 proton at a time. So for example, phosphoric acid, H3PO4. The first dissociation reaction is just losing 1 hydrogen. And then what's left over is H2PO4 minus. So that's one dissociation, but let's lose another one. Now we have this is our acid form. It still has acidic hydrogens to give away, so it is still an acid. It could lose 1, and now we give away another hydrogen, and we have what? HPO4. This should have a -2 charge, so on and so forth. guess what? HPO4 could also lose the final hydrogen. And then you'd have PO4 3 minus the phosphate anion left over. Okay. So this is losing the first hydrogen. This is losing the second hydrogen. And you could even draw, and I just ran out of room, losing the third hydrogen as well. All right, here's a great question. If an acid has multiple hydrogens, and let's say not all of them are acidic, how would you identify an acidic hydrogen? This more so applies to organic chemistry. And so what is the difference? I didn't know there was more than one kind of chemistry. In fact, there's like 5 kinds of chemistries. Inorganic, organic, biochemistry, blah, blah, blah. But only hydrogens that are bound to electronegative atoms, such as oxygen, fluorine, chlorine. You guys should be very familiar with the electronegativity chart by now. So only the atoms that are the hydrogens that are bound to electronegative atoms are acidic. So only when you have a positively polarized hydrogen is that an acidic hydrogen. In organic chemistry, it is often the hydrogen bound to oxygen. I'm gonna prove it. Okay, prove it. Okay, I will. Acetic acid, lactic acid, citric acid. These are all organic acids. What is an organic acid? Okay, an organic acid is an acid that has carbon. Carbon is what makes things organic. You and I are organic people because we have carbon in us, all in us. Food, okay, those things are organic because we have carbon in it. If you notice the acids up here, HCl, HNO3, sulfuric, phosphoric, we call those inorganic because there's no carbon. Okay, so the presence of carbon is what makes things organic. So acetic acid has some carbon in it. Let's draw acetic acid, CH3, COOOH. There's acetic acid. So based on what I just said, which one of these, we've got 4 hydrogens here, but I'll give you a hint, not all of these are acidic. Which hydrogen? There's one hydrogen that's acidic. Which hydrogen is it? Yep, the one on oxygen is what we just said. So I'm gonna, that one right there, that one's acidic. Okay, we could draw the little positively polarized sign on it. Okay, what about lactic acid? What is lactic acid? Why is lactic acid important? You health professionals, you sports medicine people, you pre-PT people? You're good, Savannah. What is lactic acid known for or used for? Or bone build in muscles. Yeah, making your muscles sore. Y'all, I do like to exercise, but I don't know what happened in October. I just got off the exercise train and I'm trying to get back on it. So I did one workout. And how many of you know that first workout back, you're sore for, you're good, Brennan. You're sore for like 3 days. And that's what happened to me. Okay. The lactic acid got me for sure. So let's draw out lactic acid. CH3, CH, and then we have this OH group in parentheses. So I'm going to branch that whole group up. And then we have another C. And okay, anytime you see a COOH, that is not this, because this carbon is going to be left deficient of number of bonds. It only has 2. We can't draw it like that. So how do we draw? COOH is a very common group you'll see in organic acids. It's got to be like this, a double bond and then an OH group. Okay, so there's lactic acid. And we should have multiple hydrogens here that are acidic. Okay, this one right here is bound to oxygen as well as this one right here. So we have 2 acidic hydrogens. None of the hydrogens bound to carbon are acidic. Okay, never tell me that a hydrogen bound to carbon is acidic because it's not in a polar bond. Carbon's not electronegative. I want to introduce another way that we draw molecules because it's more of an organic type of drawing. You'll see that actually with this picture over here. This is citric acid. We're going to draw citric acid, the Lewis structure for it. But if you Google lactic acid or you Google citric acid, you're going to see pictures like this. If you Google chemical structure or chemical formula or whatever, You'll see structures like this. What in the world is this? How do we read this? This is the same type of thing. You can get the same knowledge out of this structure as you would the Lewis structure. You just have to know a couple things. Anytime two or more lines come together, there's a carbon there. So I want you to actually draw in all the carbons on this structure, two or more lines. Anytime there's like a joint. So right here, you would have, I'll do it in a different color so you can see it better. There would be a carbon right here. Two or more lines come together. There should be a carbon right here. There's a joint. Another one. Another one. Here's another carbon and another carbon. Okay. So there is actually 6 carbons in this structure. And knowing that, it's very common for people to just omit the carbons. And in these kinds of structures, they omit the lone pairs. We should have lone pairs on all those oxygens to draw structures to just simplify them a little bit. Okay. So I want you to be, so if we come back over here and we were to draw lactic acid out like that now, how would we draw lactic acid? Well, you would start with a line that is going to represent these 2 carbons. Boom. So there would be a carbon right here and a carbon right here. And then I'm going to angle my second line so that there's a, you can tell it's 2 different. There we go. Okay, there's the 3rd carbon. And then we would have a double bond to oxygen, the OH group here. We would have the OH group sticking up right there. And we don't draw the hydrogens in. That's another thing about these kinds of structures. So if there is a carbon right here, the number of bonds it's missing is the number of bonds we have to hydrogen. So we see the bond to this second carbon over here. This would be carbon number 2. This would be the first carbon. The number of bonds this first carbon is missing, we only see 1 bond. We've drawn in 1 bond to the other carbon. We're missing 3 more bonds. So that must mean that there are 3 hydrogens attached. And indeed, there are over here. But that's how these structures work. We don't draw the hydrogens in unless they are on like an oxygen or a nitrogen or something like that. So anyways, I just wanted to introduce that to you. You're not going to have to, I don't think I'm going to make you draw stuff like this out on the exam, but I want you to be familiar with it, because if you Google something like this, you'll see structures, especially for vitamins and minerals, you'll see structures like this. And I just want you to know what that means. Okay, so anyways, we won't take the time to draw out the Lewis structure of citric acid because we've spent a lot of time on this already, but let's look at the structure over here. I want you to circle all the acidic hydrogens. How many acidic hydrogens does citric acid have? Four. That's correct. I'll circle them in red, or I'll underline them. 1, 2, 3, 4. So I don't know if we'd call it a quadraprotic acid. I actually don't know how they would name that. But there's 4 that it can give away. Okay. Questions so far on how to identify acidic hydrogens, especially on organic acids. All right. So that's it for acids. Now let's talk about bases. When an acid donates H+, something has to accept hydrogen. We just don't donate it into oblivion. Something has to pick that up. And that is where the base comes in. Okay. So the base is it accepts the H+ ion, the hydrogen ion, from the acid. And remember, bases have to have a lone pair to do that. So if you have no lone pair in your molecule, then you have nothing that it can bond to. So it's a substance that accepts hydrogen ion from the acid. So because of that, we often call it the proton acceptor. So the acid is the proton donor, the base is the proton acceptor. And so far, if we scroll back, I'll come back in just a second. Like up here, water was the base. Up here, water was the base, accepting the hydrogen both times. So you don't typically think of water as a basic substance, especially with regards to pH, and we'll get to pH later. But water can indeed act like a base. It just depends who it's around, okay? You ever met somebody that they act different depending on who they're around? That's water, okay? What is the H plus likely to bond to attach to on the base? I think we answered this already. It has to be electrons, okay? So that's why you have to have what we say a lone pair. But I've really already stated this. So I'm gonna give you two very common bases. The strongest base that's out there, and then another very common base. The strongest base we know of is OH minus, hydroxide. Hydroxide is an incredibly strong base. Why? Two reasons. One, this oxygen here has actually 3 lone pairs attached to it. So there's a plethora of lone pairs for this hydrogen, incoming hydrogen, to pick. And overall, the thing's negatively charged. And we know the hydrogen ion that's coming in and is going to bind to this is positively charged. So there's an electrical attraction as well. So we've got 3 lone pairs, and it is negatively charged. So hydrogen ions are really attracted to that. So that's 2 reasons that it's a really strong base. You often see hydroxide in the form of bound to a metal. So the way you'll see the base, like in a chemical reaction, is you'll see like LiOH or NaOH or CaOH2. Okay, calcium hydroxide, sodium hydroxide, lithium. These are very strong bases. Okay. Now the metal, the lithium, the sodium, and the calcium, they don't play a part in the acid-base reaction. They're just initially attached to hydroxide. They're kind of what we call the spectator ion. They're just there to watch. They're not participating in the reaction, okay? So they'll actually disassociate from hydroxide, and then hydroxide will go do its thing and act like a base. And how would they accept a hydrogen? So if we have OH minus plus H plus, again, here's all our lone pairs. These lone pairs are going to grab that hydrogen up, and we're just going to make water. Now, if you see it like lithium hydroxide, what I was saying earlier, plus H plus, same thing, you're going to make water. The hydroxide and the H plus make the water, and then you'll just have lithium left over. You just write it like that, okay? Lithium being what we call not participating in the reaction. All right, a second base, though, that's a very common base, is NH3, ammonia, NH3. Ammonia is a very common base. It's not as strong as hydroxide. It's a weaker base, but it's still a good base. You see it used a lot. So what happens? How does it accept a hydrogen? Well, NH3 plus H. Where's the lone pair here? We got to have a lone pair, right? Draw out the Lewis structure of NH3. Where's the lone pair? It's got to be on the nitrogen. So there's a lone pair on this nitrogen. You can draw it right there. And that lone pair is going to accept the H plus. And what are we going to make? Ammonium ion, that's right, NH4 plus, okay? So those are 2 different examples. Now, one thing I want to point out is with bases, you can have bases that are already negatively charged, or you can have bases that are neutral. Hydroxide is a good example of one that is already negatively charged. I didn't really leave myself space here, but we wrote that actually, negatively charged. So when it grabs the hydrogen ion, your resulting product is neutral. Okay, water is a neutral substance. We know that. There's no charge overall. You put together a -1 and a +1, they neutralize each other. That's why, remember in chapter 5, we called them acid-base neutralization reactions. Okay, they neutralize each other from a charge standpoint and from a pH standpoint. And we'll get to pH later. But you can also have bases that starting out are neutral. NH3 is neutral starting out. And when you add the hydrogen ion, what you end up with is a positively charged product. Okay, you have to keep track of how charge changes. If you are adding a hydrogen ion to something, then you are increasing its charge by +1. Okay, so bases always increase in charge when they accept that hydrogen. They may go from -1 to 0. They may go from neutral 0 to +1. They could go from -2 to -1. The point is that their charge increases by 1 if they accept 1 hydrogen. These are the textbook pictures of what we just walked through. Okay, there's ammonia. It's a neutral base. Shows you the lone pair grabbing that acidic hydrogen off the acid. We often abbreviate acid as HA, and I think I explained that back in chapter 5 somewhere. HA, A for acid, and then we draw the acidic hydrogen in. And then here's your ammonium ion, positively charged product, and here's the leftover portion of the acid. Okay. These electrons right here, they stay on the acid. Okay. The acid grabs those up, and then the hydrogen leaves with no electrons and binds to the lone pair on the base. All right. And then here's the example from your textbook with the hydroxide ion, what we just drew out. All right. Questions so far on how acids give away protons and how bases accept them? Surely there's a question. Okay. Well, just to recap what I just said, acids lose a H+, so they decrease in charge. Neutral acids become negatively charged. Example, HCl. You give away the hydrogen ion, you have Cl- left over. Acids with a -1 become a -2. What's an example? If you have, well, H2PO4, we drew this one earlier, negatively charged. If that gives away a hydrogen, we are left with HPO4 2-. Okay, those are just examples. They're always what's left over from the acid is reduced in charge by -1. Bases gain a hydrogen ion, so on the flip side, they increase in charge. So a neutral base becomes a +1. That's what we saw with NH3. I gotta draw the hydrogen. This probably feels redundant, but I promise we're going somewhere with it. And then bases with a -1, that would, prime example, hydroxide, become neutral. Okay. And then this is just a good recap. This is again a figure from your textbook. So the biggest thing with this chapter is do not ever mix this up. It's the acid that's donating. It's the base that accepts the proton. So we need to redefine acid-base reactions. In the past, I told you that an acid-base reaction makes what? How did I want you to identify an acid-base reaction back in chapter 5? This was exam 2. I had you classify precipitation, acid-base neutralization, and redox reactions. And I said, you'll know it's acid-base if it does what? You'll know it's an acid-base reaction if it produces salt and a water. Can you scroll back up very quickly? Yes. Yes, Kathleen got it right. If it produces salt and water, then we said that's acid-base. However, we have to, and that's not wrong, but it's not inclusive enough. It's exclusive. So we need to, is that good, Aaliyah?
Yes, ma'am.
So we need to broaden our definition. An acid-base reaction is one in which a proton is transferred. Okay. It's a reaction in which a proton is transferred. Oops. There we go. I like these figures down here. We always abbreviate base with a B and they color it in blue. We always abbreviate the acid HA, and they always color it in red. And these just show you this is a neutral base. This is a negative base. It just shows you how they're grabbing the hydrogen from the acid and the products that they make. This product is neutral now, and this one is positive. Okay, so we're just highlighting the changes in charge as you trade a hydrogen ion. Okay, let's do some practice now. We're going to do the first one together, and then I have a poll questions for the next two. So I want you to identify the acid and the base in each of the following reactions. This is a very good example of a type of a question I would put on the exam. Give you a reaction, say which one's your acid, which one's your base. So let's look at number one. You have to consider on the product side which substance, which reactant has gained a hydrogen. So same substance, but with an extra hydrogen in the chemical formula, and which substance has given away a hydrogen. Okay, remember the one that gives away the hydrogen is the acid, the one that accepts it is the base. So we have CH3NH2 and water. Then we have CH3NH3 plus and OH minus. So it looks like CH3NH2, same formula, just with an extra hydrogen on the end there. Okay, and it is increasing in charge. It's neutral here, and now it's +1. So we know bases increase in charge. They accept hydrogens, so this must be the base. Okay, you don't think of water as an acid, okay? But remember, water will play the role of an acid or a base depending on what it's around. So here it's in the presence of a base. So that means water, H2O, when we lose a hydrogen, what's left over is OH minus. So this is the acid. So the lone pair on this nitrogen is grabbing one of those hydrogens, and that's where you get your products. Okay, so I'm going to launch the poll, and I want you to do the same style of thinking towards number 2 and number 3. In reaction 2, which component is the acid? I could not do subscripts or superscripts, so I'll put the subscripts in the formula and the charges in parentheses, unless it was OH minus. So think about what gives away hydrogen, what accepts it. You got to look at the products to know that. We're about halfway, actually not really. 12 of 28 voted, 13. Get your votes in. We're a minute and a half in. I'm going to stop it at 2 minutes, so you got another 30 seconds. Brennan, what did you ask for ? About? All right, we've hit 2 minutes. We're only 75% voted. Anybody else going to get your vote in real quick? There's 4 questions. Oh, well, yeah. The first 2 are about reaction 2. The last 2 are about reaction 3. That's okay, Abby. I'm on my phone, it won't work, so don't wait on me. Okay. Share results. Okay. Reaction 2. Most people said that HPO4 2- is the acid, okay? So remember, acid gives away a hydrogen. So here we have it, one hydrogen, and on the product side we have PO4 3- with no hydrogen. So it lost a hydrogen. It's the proton donor, definitely the acid. OH minus, most people said it was the base. So we have OH and then we have H2O. So that's hydroxide with an added hydrogen. It goes from negative to neutral. So it's increasing in charge, which is another characteristic of a base. So definitely the base here. And we said hydroxide is a really strong base. So anytime you see OH minus, don't ever label that as the acid. It will always be the base. Okay, good. Reaction 3, we have HCO3- and water. Both things have hydrogens. So you can never label an acid just because it has hydrogens there. You have to look at what's gaining or what's losing. So H3O- goes to H2CO3. It's negative and now it's neutral. So that's increasing in charge. So it accepted a hydrogen. So it must be the base. Remember, a base is a proton acceptor. Water is now OH- on the product side. So it's neutral and now it's negatively charged. Acids decrease by 1. So this has to be the acid. Okay. I see that in all cases I put the base first and the acid second. I just want to clarify, just because a product is written first does not mean it's a base. Okay, I could have easily switched the order of my reactants here. So don't think, oh, it's a base if it's written first. It's an acid if it's my second reactant. That's not the case. I just happened to notice that I wrote the base first in all the cases. All right. Well, I hope that clarifies things. I will totally have you do stuff like this on the exam. Now we're going to put a pin in that, and we're going to address a different aspect of acids and bases. We're going to address what we call conjugates. So we'll get through conjugates, and then we'll do a couple of practice problems, and we might get to acid-base strength, and that's going to be it for today. So we're almost done. Hang in there. What is a conjugate? Okay, so when an acid and a base react, the result is a weaker version of an acid and a base. So your products are also acids and bases. How confusing is this? The acid that results from the base is called the conjugate acid of that base. So essentially what we're saying is you have a base in every acid-base reaction. If you're looking at the reactant side, the reactants are what you label acid and base. The products are what you label as the conjugates. And when we put a hydrogen onto this base, what we get is B plus, now with that hydrogen bound, and we're going to call this is an acid. Why? It could give away that hydrogen, but it's the conjugate. We call it a conjugate acid. So you will never label conjugates on the reactant side. Your conjugates are always on the product side. You will never label acid and base on the product side. Your original acid and base are always on the reactant side. On the flip side, the base that results from the acid is called the conjugate base of that acid. So notice what was the acid becomes the base on the product side. It's just the conjugate base. What was the base on the reactant side becomes the acid on the reactant side. And they're weaker, okay? The reactants are always stronger, more corrosive, and your products are always weaker in strength. Okay, so if we have the acid, HA, gives away a hydrogen. Now look, we have a lone pair. We're eligible to accept a hydrogen. That makes us a base. It's just that we're the conjugate base. Okay? So I want you to practice labeling conjugate acid-base pairs. If these lines that they draw in, okay, these things connecting the base to the conjugate acid and connecting the acid to the conjugate base help, then do that by all means. So we're going to practice this. What is the conjugate base for each of the following acids? So you need to think, what does an acid do? It gives away a hydrogen. So all you're going to do is essentially write the dissociation reaction for all of these acids. I'll do the first one with you, and then I want you to do the next 3 on your own, and we'll follow up. So if this disassociates, we'll get H plus, and we'll get ClO4 minus, okay? And this right here is our conjugate base. I like to abbreviate conjugate. So do that for H2S. And remember how acids change in charge. They decrease in charge. So if they're neutral starting out, they are -1 as a conjugate base. If they're a +1 starting out, they're neutral as the conjugate base. Okay, what should we have for the second one? We know we're going to give away a hydrogen. What's our conjugate base? Aaliyah, you're very close. It is HS, but you have to also remember it was neutral over here. Now it's a -1. Yeah, most people are getting it. Okay, so this is the conjugate base. pH4 plus, it gives away hydrogen. What is our conjugate base? Yep, James got it, Kathleen got it. What is our conjugate base for this third one? pH3, that's correct, Jenna, and it should be neutral. And then what about the last one? We have HCO3 minus. It's going to give away hydrogen. What is left over? CO3, and it has a -2. So it goes from -1 to -2. Remember, acids always decrease in charge by 1. So these are your conjugate base. All right, any questions there? Now we're going to do the flip side of that. What is the conjugate acid for each of the following bases? What does a base do? It accepts the proton, H plus. So draw the same chemical formula, but with a hydrogen attached. And we always throw the hydrogen onto the front, unless you want to be different and you want to be ammonia and you want to put the hydrogen on the end. Okay, well, I guess pH4 has it on the end too, but usually the hydrogen goes on the front. If you look at all these acids up here, hydrogen is the first element written. So if you're asking how do you write that, add the hydrogen to the front. So we would say plus hydrogen makes, I'll do this first one with you, HCN. This was -1, now it's 0, neutral. So we'll be adding a hydrogen to all of these. So what do y'all have for my second one? What is my conjugate acid? HSO4 minus. So Jenna got, yep, that's right. Okay, water, we've already seen it done with water. We know that makes the hydronium ion. So you should have H3O plus there. What about the last one? What do y'all get? You have HCO3 minus, you add a hydrogen, what do you get? And what's the charge on that? Yes. Hold on, Aaliyah. It was a -1, and it only accepted 1 hydrogen. Yeah, it should be neutral. You should have H2CO3. You got the right formula, but it was -1, so now it's just neutral. Okay. All right, so So far, you've learned how to define an acid and a base, how to look at a chemical reaction and label those, and now you've learned how to label the conjugate acid-base pairs. Here's another word style practice problem. It says hydrogen sulfite. We haven't dealt a whole lot with sulfite. It's the cousin to sulfate, but the hydrogen sulfide ion is amphiprotic. What does it mean if you're amphiprotic? This means you can give or receive a hydrogen. All right. HCO3 minus is a good example. It has a hydrogen it could give away, or it could accept. That's what we drew over here. It accepted a hydrogen. It's amphiprotic. It can give or receive. Write an equation for a reaction of HSO3 minus with water in which the ion, which is this guy, acts as an acid. So do part A. You have HSO3 hydrogen sulfide with water, H2O, and we're saying this is the acid. So what are your products? That's the acid, water is the base. So this is going to give H plus, this is going to accept. So you should get SO3 minus 2, and then you should get H3O plus. Keep in mind how the charges change. Bases always increase by 1, and charged acids always decrease. So now can you label the conjugate acid-base pairs on this? Because that's what I say at the end. In both cases, identify the conjugate acid-base pairs. So SO3 minus 2, is that the conjugate acid or the conjugate base? What do y'all think? Think it's the conjugate acid? I'm gonna draw those connecting lines like what we saw earlier. That's connected to that, and this one is connected to the hydronium. It should be the conjugate base, yeah. We're gonna have lone pairs all over those oxygens, even though you can't see them. All right, so then water is the base, so this must be the conjugate acid. Okay, part B says to write an equation for the reaction, same ion, HSO3 minus with water, in which the ion now acts as the base. Because it's amphiprotic, it can be acid or base. So now we're saying this one's going to be the base, and this one's going to be the acid. Oops. So what products would you get now? Well, if water is the acid, it's giving away a hydrogen. We're going to be left over with OH minus. And if HSO3 minus is the base, it's receiving a hydrogen. Yes, Jenna, H2SO3, and it's neutral. So we went from neutral here to -1 there, because acids decrease by 1, and the base was -1, and now it's neutral over here because bases increase by 1. And if you had to label the conjugate acid-base pairs, what is OH minus? What is the hydroxide? Should be the conjugate base. And H2SO3 is by default the conjugate acid. Okay. All right, I feel like we've done quite a bit of this. So I want you to know how to label conjugate acids and bases. I want you to know how to write them. If I just give you like up here, if I just give you a substance and say, write my conjugate acid or conjugate base, and then I want you to look at a reaction and be able to label the pairs as well. All right, we've got like 10 minutes left. We're going to hit acid-base strength, and then we will have covered everything I want to cover today. So we won't take long on this. We're almost there. I want to ask you a question. HCl and vinegar, they're both acids. Okay, vinegar has acetic acid in it. Which one would you be willing to drink, essentially? If I gave you a cup of HCl and a cup of vinegar, this is a dumb question, right? Which one would you be willing to ingest? Vinegar, okay? People cook with vinegar all the time. You have vinegar in salad dressings. You have vinegar in different recipes. So we're fine with vinegar. Why would we not want to ingest HCl? We know HCl is highly corrosive, and vinegar or acetic acid, that is the acid in vinegar, is edible. Well, why? It all depends on acid-base strength. They're both acids, it's just that one is less corrosive. The stronger an acid is, the more corrosive it is. So it must be that HCl is a much stronger acid than vinegar, and you're right if you think that. So it depends on, and all that depends on how easily the acid disassociates. Essentially, how easily does it give up the hydrogen ion? So here's our two acids, HCl and vinegar. And we know HCl we've labeled it as the strong acid. We would not want to ingest strong acids. Vinegar is a weak acid, and our bodies can handle weak acids. Now, I know what some of you may be thinking. We have HCl in our body, right? It's in our stomachs. It is stomach acid, HCl is. And you're right, but we probably have a very low concentration of it. I'm not exactly sure what the concentration of HCl in our stomachs is, but HCl is what helps break down your food because it's corrosive. It corrodes anything we give our stomach. So, but that still would not make me want to drink HCl. Please don't do that. Okay. So how do we differentiate strong acids versus weak acids? A strong acid is going to completely give away every hydrogen. If I have 100 molecules of HCl, every single molecule will give away hydrogen. You will not have any molecules of HCl left over. All 100 will give away hydrogen, so you will get all products. If I started out with 100 of these and 100 of water molecules, I would end up with 100 H3O plus. So initially I start out with 0. So I'm just going to say initial. And then final. Final amounts would be, I'd have 0 of these things left over. I would have 100 of these. And then I would have Cl minus left over. 0 and 100. Oh, Google says HCl is about 0.5%. Okay, well, if you buy it as a stock solution, you guys remember dilution problems, you normally buy things as stock solution, it's 12 molar, okay? So 5% is very small percent compared to, I'm not sure what percent we would give 12 molar or what molarity, we could calculate that, but we'll do that on a different day. But all that to say, that proves the point. Stomach acid is a low concentration. Okay, so anyways, strong acids, the key thing here that I want to point out is you get a single arrow, which means you have no reverse reaction. You have none of your products combining together to remake your reactants. If I give you a reaction, you will know it's a strong acid if it has a single arrow, because you're gonna make all products. Weak acids, on the other hand, guess what? They have the double arrow. So acetic acid, this is the acid. Water is the base. So what products would we get? Here is our acidic hydrogen. We're going to give that one away. So we'll have CH3COO minus would be the conjugate base. And then we'll have H3O plus, sorry. There we go. And what we did up here with saying initially I have 100, now I have 0, we can't do that with the weak acid, because you're going to remake some of your reactants, so you don't know. You don't exactly know. Initially, if we have 100 and 100 of these, and initially we start out with 0 of these and 0 of those, final, we can't say, oh, it's going to be 0 and 0. We don't know. We actually don't know. Okay, it could be 50, it could be 40, it could be 60, it could be 70. you're going to get some number. You're going to have numbers all the way across the board, and they won't be 0 and they won't be 100. It'll be somewhere in between. And we get a double arrow. You've seen a double arrow before. Where have we seen the double arrow? What did we talk about? Where did we introduce double arrows? Anybody remember? In chapter 7? You're like, no, I chose to forget chapter 7. I hate chapter 7. Yes, reverse reactions, equilibrium. Okay, so we're going to actually come back to equilibrium because we have equilibrium systems with weak acids, but we'll save that for a different day. Guess what? If acids have relative strengths, bases do as well. Strong bases have a high affinity for H+. They really like to bind H+. Prime example, OH-, and I gave you 2 reasons earlier for why it likes to bind H+ so much. You've got 3 lone pairs on that oxygen, and you've got a negative charge. So there's an electrical attraction to things that are positive. Weak bases have a lower affinity for H+. They still bind them, but just not as much. So if you're in the presence of a strong base, you bow to that base. You give it all your hydrogens, okay? So water here is the acid, and if there's 100 NaOH molecules, it's going to take 100 hydrogens from water. So remember, this is actually going to dissociate into Na+ and OH-, and it's the OH portion that is the strong base here. So OH-, when we add the hydrogen that we take from water, it's going to grab a hydrogen from water. You're going to make H2O plus you're going to have OH-. This looks very redundant because you have OH- and H2 on the reactant side. But that's when you trade the hydrogen, that's what you get. And then you'd have the spectator ion, sodium ion over here. Okay. The key thing here, though, just like with strong acids, is you have a single arrow. This is one directional, no equilibrium here. With weak bases, you get the double arrow. This is the base. Water is the acid. What products do we get? NH4+ and OH-. And again, the key thing here is that we're going to have an equilibrium because it's a weak base, and that's also what weak acids do. They don't, you'll have these products rebump into each other, retrade the proton back to get your original reactants. All right, any questions so far on acid-base strength? Here's a table from your textbook. You'll have this table on your resources page for exam 4. Do not take your time to memorize these things. I don't need you to memorize what are the 6 strong acids and what is how many weak bases are there. You just know this is available to you. Here's how to read it. On the left side, the red side, these are all your acids. And down at the bottom, you have all your weak acids, or I should say very weak acids. Then you have your less weak acids, and then you have your strong acids up top. So guess what? As you go up the table, you're becoming stronger and stronger and stronger and stronger. There are 6 known strong acids that are listed up here at the top. Several of these we've already introduced today. All right, guess what's at the bottom? Water. We don't really consider it an acid. It just can play the role of an acid if it's in the presence of a base. On the flip side, the blue side is your base. And we have the weak bases up here. And as you go down, you increase in strength. All right. And remember when we talked about conjugates anyways, if you notice in here, on the left side, you have the chemical formula, and on the right side, you have the conjugate. Losing the hydrogen, making the base, conjugate base, and that's why it listed conjugate base. Of all of these different acids, you have the conjugate base listed, okay? So water is a very weak acid, and it's also a very weak base. We know that. It's really not one or the other. It can be both. All right, any questions on how to read this table? So guess what? For any of these, you could write an equilibrium expression because you're going to have the double arrow for any of these weak acids. So that's something to know. All right, I think that's as far as I think this is as far as I want to get today. Okay. We'll start with the acid dissociation constant on next week. Today's, Thursday. Any questions from you guys? I would love to hear. I know it's been a minute, but I wanted some feedback on what y'all thought about the study guide for exam 3. I meant to ask this